Welcome back. The last talk this morning is Matthias Seeger, and he's going to tell us about large-scale inference.
So I'd like to thank you very much for inviting me. I've been back here in February giving a talk about very similar things, approximate inference, experimental design, and even back then I had a very particular application in mind to apply this to, and but I knew back then that the algorithms were not up to the scale that was required there. And I mean, since then things really fell into place, so I can show you now some very recent results I'm quite excited about, actually. So this is the outline of the talk. This is going to be about the sparse linear model. Once more, we've heard a lot about that model in the course of that whole program. But I think I have a little bit of a different thing I'm going to do with them, which is experimental design. I have not heard talks about that so far here. So experimental design in the Bayesian sense needs Bayesian inference in the first place, and we are going to approximate it mainly for scalability and tractability reasons. And I'm going to talk about variational approximations, which are deterministic as opposed to Markov chain approximations. Now, even the algorithms we had so far were not up to really big problems, and so I'm going to talk about some scalable algorithms that can really go into, I guess, into new domains that were not accessible before for these algorithms. And really, you need these. Okay, that was the wrong one. So these algorithms are then really needed to address an application I really have in mind, which is actually optimizing control sequences for magnetic resonance imaging. So this is kind of the abstract view on the problem that I really want to address here with using statistical methods. You have an image over here. This is a lady very often used in computer vision, Lena. And so you have an image which you just view as a vector, n pixels. And then you get noisy linear measurements of that image. So X is basically the filter matrix that you apply to measure this image. Then you get responses and you have some noise. In our case, it's Gaussian noise. So I apologize. This is n usually in most talks, and this would be p. Now in this case, n is the number of variables, number of pixels, and m is the number of measurements. It's just to confuse you. And really the goal here of the whole enterprise is to, from these measurements, reconstruct the image. And applications of that are, for example, a lot of them are in digital photography, but also a very interesting application area of that is medical imaging, magnetic resonance imaging, for example. So of course, it's a very important problem and very well-studied problem to, once you have the measurements, you actually reconstruct you in a very good way. And recently there's been a lot of attention how you can actually apply prior information you know about signals like images to do that job very much better than it was done before. But there's a second problem, I think, which is almost as interesting, I think, and should also be considered to be very important. Namely, in the first place, how do we measure at all? I mean, what filters do we apply to the unknown image so that we can reconstruct it well? So do you go for standard solutions, like in the JPEG compression standard, you just encode wavelet coefficients in a fixed ordering? Do you just measure these guys? Or I mean, some recent theory seems to suggest that you can get away by just applying random filters to images to measure them. That would be simpler in a sense. Or do you actually optimize the way that you measure? Do you choose these filters in some sense, in some good way? So if you want to do that, what criterion do you actually optimize? Where does that come from? Well, we are going to work our way towards one possible solutions for this. And this is the linear model. I don't really have to say much about this. This is a noisy linear equation. Latent variables here, n of them, pixels of an image, think about that. Measurements, responses over here, the design matrix X. We have Gaussian noise, which for the moment is really simple, just independent Gaussian noise. You can generalize that. No, I guess if you open a textbook a Bayesian textbook about linear models, this is basically what they tell you that you can do. Certainly you can do this because it's very, very simple. You use a Gaussian prior on the latent variables. If you do that, the posterior is Gaussian as well, and you can write down all these things analytically. So really people use the Gaussian prior very often with the linear model, but one of the main reasons why they do that is because it's just very simple to do. I mean, we had a talk this morning where basically exactly my opinion on that was also on the slide. I mean, Gaussian distributions are not informative. They are maximum entropy distributions. So basically, think about them of not enforcing anything very strongly. Certainly, in the case of images I want to get to, they don't enforce sparsity very strongly at all. And one of the main reasons why they actually cannot enforce sparsity very strongly is somewhat surprisingly because they don't allow any large coefficients. They don't have heavy tails. So maybe this is one of the most important lines in the whole talk. Whatever images are, if you want to work with images and if you want to apply statistical techniques to anything with images, just never forget that they are absolutely not Gaussian at all. Now, okay, so what is the distribution of natural images? This is probably something that we will never answer, but one very, very useful thing about this distribution is that we know some characteristics, some very robust characteristics of this very complicated distribution, which are actually very simple to describe. So it's kind of a partial knowledge, and we can exploit that nowadays to do a better job with images. So one thing, for example, people figured out is that if you do certain transforms, certain filters, let's say a wavelet transform, and you look at the coefficients and you plot histograms, then they have very super Gaussian distributions. So this is, for example, a wavelet transform of Lena. This is on a log scale, otherwise you wouldn't even see this down here. And you have a very high concentration of the energy up here, and if you plot that, you get a spike here, but you also get heavy tails down here. So this is super Gaussian distribution. Another thing you can do, and we had this in Professor Tibshirani's talk, I think he called this the 2D lasso, you just can look at nearest neighbor differences. And basically they are, again, super Gaussian distributed. People in image computer vision call this the image gradient because it allows you to find edges in an image. So you filter nearest neighbor differences, and when they pop up, then you have an edge. You can do this to second order and so on, and this gives you a whole amount of filters you can apply to an image, and always super Gaussian distributions pop out. You will never see any of these things being Gaussian if you don't look at noise, if you look at natural images. So if you then want to put that into, yeah?
So looking at distributions at all suggests some kind of stationarity.
Okay, so you know, I mean, okay, this goes way, I mean, in a prior you can always encode this and this much. So you can encode, for example, you can encode super Gaussianity in a prior, but forget about dependencies. You can go further and you can encode dependencies. It goes a little bit to the remark that I said. So if we want to describe the distribution of natural images, we are probably not ever going to get there, but we can try to go stepwise. What I'm talking about here is not going to talk about dependencies between these filter coefficients. You could do that, but what I'm showing probably in my results is that you don't have to do it to get a huge gain in some performance gain. But you're right, I mean, of course, there are very intricate dependencies between these filters, and if you model them, maybe you get even better. So in that sense, it's okay, I'm just showing you in a second what that prior is, and it will be, in a sense, what you would call a stationary prior. So if you want to encode that knowledge, you need super Gaussian distributions. The Gaussian won't do it. So for example, you could take something like the Laplace distribution, which basically just has the characteristic of a sparsity prior in that it really allows a few of the coefficients to be large. It has heavy tails, and that then allows it to force most of the coefficients to very small values. Basically, if you take the log of that, you have L1 penalties like that they are used in lasso. In a Bayesian context, this image really shows you what's going on. So this is a prior, just seen from above, and this is one noisy measurement, which is like a tube going here, and the posterior is obtained by multiplying that, renormalizing. In a Gaussian case, you see that the mass really is just spread like an ellipse, and there's no concentration visible towards the axis, while if you do the same thing with a prior of same variance, which is a sparsity prior, you have a shrinkage in the posterior mass towards one of the axes. And this happens even much, much more in high dimensions. This is probably a little bit analogous to this geometry properties in estimation. I don't know much about that. So I mean, this is not the only sparsity distribution. So you might have encountered at least one of these things up here. There's these spike and slab distributions, which are basically mixtures of two Gaussians, one very narrow, one very wide. You can do that. There's the student T distributions for small degrees of freedom. They also induce sparsity just by their heavy tails. And the Laplace is part of this power family where you can also select other members. Laplace you get by setting alpha to 1. If you set alpha to 2, you have the Gaussian. And in general, if you have alpha 1 or smaller, then you would say that this is sparsity inducing. As I already mentioned, so all of them have heavy tails, so they allow outliers in a sense, so they can really enforce sparsity on the others. They are all scale mixture distributions, which is actually going to be important for the approximate inference. And among all these candidates up here, there's maybe one difference that is important in practice, that only the exponential power distribution with a power larger or equal than 1 are actually log concave, which means that if you do Bayesian inference with them, the posterior will only have a single mode. And that really is easier to deal with than if you have multiple modes. But for this talk, it's not so important that we have that property. So what is then Bayesian experimental design? So again, I repeat the model over here, and this is what we want to do. There's this really nice analogy to explain what that means. I'm saying standard machine learning, but you could probably also replace machine learning by statistics here. It's a little bit like if you're teaching a very sullen, non-responsive student, you really have to teach him some material, or and you have to come up with a lot of examples, positive, negative ones, and the student always looking at you, never giving you any feedback. You know, did you understand this? I don't know. Did you get that? What was it you didn't get? What do you need more explanation for that? You never get any feedback, so you have to do actually basically almost all the work yourself, and in the end you get an estimator that does then, you know, runs maybe in a millisecond, but you have to spend a lot of work up here. Experimental design is actually, in that analogy, it's a little bit like a very active student, very responsive. So she's going to, you know, tell you what she didn't get, and then it's very much easier for you to come up with the right examples because you're basically getting the feedback. I got that, I didn't get that so well, and this is much more fun, and this is also much more efficient. So efficiency is the important thing about design. And if you then look what that means in practice, it means that the machine, okay, we always talk about machines, really asks you for the data exactly where it needs more. And also it adjusts its features as it goes on. So formally, Bayesian sequential experimental design works like that. Really, it's about these three questions. How much do I already know at the moment? You have to answer that question so that you can then make good decisions in the future. You have to know what do you already know. Now, in Bayesian statistics, this is just the posterior, okay? The distribution of the latent given the observed. Or if you want to have a single number, it's the entropy, for example. So then you have to ask, okay, so if I had another data case here, so how much would that actually help me? So it would make the posterior sharper with almost all these models that we consider. So you can actually look at the posterior before, which is the entropy here, and then you can look at the posterior after you've done that experiment, can take the difference. This is one possibility that we are going to use. This is not quite realizable because, of course, I mean, you would like to do that experiment here, but you don't know the outcome. And then the vanilla Bayesian idea here is to integrate everything you don't know, you integrate it out. So from the question, how much would that help, you can really go down to something that is realizable. So how much will that experiment help me? In Bayesian terms, the answer is just take the expectation over the posterior of the outcome. And this is basically what we call this Bayesian design scores. And the real motivation for doing Bayesian inference in these contexts is really only to compute these numbers as quick as possible for many candidates. So then you can make these decisions which are within the framework optimal. So let me just, this is important, reiterate why I'm doing all this here. This is, it's not a religious enterprise. It's really something that's motivated by the problem. Really, I think that fundamentally, if you want to do experimental design, you need to somehow quantify your uncertainty in as good a way as possible. And the Bayesian posterior is maybe just one idea where how you can do that. Maybe there are others. And if it's infeasible, well, we are pragmatic, then we are just going to use some approximations to it. Now you might know that Bayesian experimental design is completely tractable for the Gaussian linear model. And I highlighted Gaussian here. So actually, for that, you wouldn't need any approximate inference in the first place. So why am I not using that? Well, this is again the most important line. Images are just not Gaussian. If you ignore that fact, then you will just fail when you work with images. I think I can say that like it's here. And if you want to have an analogy, this is much like, in the same reason why least squares estimation fails when you have many less measurements than variables. It's just the same. You're ignoring very important information here. And the second thing is that for the Gaussian linear model, something very unusual happens in that a sequential design in which you actually ask for new information and you get back to you, and then you optimize your query again and you ask for more information. The sequential design is exactly the same as the a priori design. And this is basically, I think, more or less, one could discuss about that, but I think this is more or less a flaw of the model. It shouldn't really be like that. So in fact, the sequential design would then actually never use any responses that I get in between. Okay, now how are we actually going to do this? This is very high dimensional. Image have a lot of pixels, and we need to do Bayesian inference on very high dimensional latent objects. How are we going to do that? So this is the posterior formally. So this is the Gaussian likelihood here. This would not really be a problem if it was only that. It's these guys that are the problem. So this is basically potentials, I call them, or sites, which are sitting on one-dimensional coefficients which themselves are linear in the image. So think about wavelet coefficients here, part of that S, or these nearest neighbor difference, or other filters that you might want to penalize in an image to be super Gaussian. And these sites are actually not Gaussian, they are super Gaussian. And I know that we just cannot do integrals once we have any of them. If we have a lot of variables over here, and if we have quite a few of these guys here, it just becomes intractable. So one of the standard ways of now proceeding is to approximate these distributions by Gaussians. So one way of doing that is basically to take each of these non-Gaussians and formally replace it by a Gaussian term. So just take that one and we replace it by something which is e up to the quadratic, where this guy is not negative. Now this introduces new parameters, and these are the parameters we are going to optimize over. And this is what variational inference in that context actually means. Nothing more than that. So you get a Gaussian approximation to the true non-Gaussian posterior, which you can write in that way with a covariance matrix and a mean, which is basically exactly that, because if all these terms are Gaussian form and this is Gaussian, you get a Gaussian again. And then you're just going to approximate all these new parameters that you get, quite a few of them actually, to approximate actually the joint posterior over here. Don't think about approximating the single sites sitting up here individually by little Gaussians. This is a very wrong idea. You're going to approximate this guy over here, which is a very complicated coupling between this coupled likelihood and these not even independent sites, but in a sense what you would maybe call stationary. So then what do I mean with approximate the joint posterior? What is actually the problem that I really want to solve? What is the optimization problem? And once I have that, what is the algorithm that I'm going to do? So one idea to actually get to the optimization problem is just the variational one. And to understand that, you have to basically know about this one function, which is very important in all this business. It's the partition function, and another way of looking at it is the marginal likelihood. And then some people even call it the evidence. Simply the integral is basically, I like this term because basically it's just the marginal likelihood of your data. You've integrated out your latent variables. That's what it is. So what? That's just a number, right? Okay, what can I do with that? Well, the important thing is it's not just a number, because in a sense, it's a function of the data. And the nice thing about it, if you view it in that way, it becomes just the moment generating function of the posterior distribution. So in a sense, all the posterior moments that we really want to get out of this game, they are in this function already. You just have to take the appropriate derivatives of it. So we need to control that function in a sense. Now in variational methods, many of them, they just go away and bound this function from below or from above. And why should I bound this function? Well, there might be many reasons for doing that, but a very compelling one is that if you have a lower bound, which depends on these parameters, an algorithm almost immediately pops out because you then maximize this lower bound, you get closer and closer to the truth, and you have usually you have convergent algorithms for that. You just have to make sure that they increase in every step. Then you have an upper bounded function and stuff like that converges. So how do we get bounds actually? So this is a very, very general technique if you spot convexity in any functions to actually get bounds. This is called Legendre duality or also Fenkel duality, which simply just stems from the fact that, you know, what does convexity actually mean? It means that you can lower bound a function by linear functions which touch the function at every point. That's equivalent to saying that the function is convex. Now, okay, so once we have that definition, we can use it because we can parameterize all these linear lower bounds. We can parameterize them by basically their normal vector or their slope, and the offset that you can read off here at 0. So we just put that. So here we have 0, and then we have something here. So we get a point over here, and that is actually going to get us this what we call the dual function to the convex function we started from. Now we can do this at several points, get several lower bounds. You see that if I do it here, then we have then I'm over here. How do we get this line? Where we simply observe that suppose I want to now know what all these lower bounds do with respect to this one point here. Now they're all lower bounds, so if I evaluate them at this ordinate here, then I always be lower than that point. And exactly the one tangent here where it touches is going to maximize all these evaluation points here. So that is how I get this thing here. So I get back the function as a supremum over all these lower bounds. Okay, I can do that here. So that is going to get me down here. This is not even on the slide, but this one is going to get me the highest one. This is going to realize basically the function value back here. And when I trace that over here, then I get another convex function, which is the dual. And this is really a duality because you can just do the same thing starting on that function and you retrieve that function. And this is actually the main mechanism to get these lower bounds in these setups. I'm not sure if many people are aware of that, but this technique is at the heart of very, very many techniques that we use all the time. I'm just listing a few of them here. Expectation maximization is a direct application of Legendre duality. If you write it in the right way. If you learn Markov random fields, if you want to know log linear models, you want to know the parameters, there's methods called iterative scaling. This is just Legendre duality. Exponential family mathematics is much just about Legendre duality. If you want to go from natural and moment parameterizations back and forth, this is just a jump from the function to the dual function and back. Bregman divergences are basically defined on top of Legendre duality. Now I'm going towards what we are doing with that stuff. Variational mean field approximations can be seen, the whole variation equation is basically a Legendre duality, a very specific one. We had a talk by Professor Zybakov on peg Bayesian bounding. This is just Legendre duality. The main idea behind that technique is Legendre duality. And I mean, I could continue here, but so we are actually going to use this trick twice now, quite in a different way. First time we use it is basically to get that first step. We need to bound that non-Gaussian guy by a Gaussian guy. So what we are going to do is, so this is the Laplace here, and we realize certainly that it's a symmetric function. It sits at 0 and looks the same in both directions. So we can also view it as a function of Sj square. And we take the log of it and whatnot. And then we see if we do that, then this g function, if you view it as a function of x, is actually convex. So then we can apply Legendre duality because the exponential function is monotonic. We still retain that inequality here. So we get something over here, which is linear in x, so it's actually quadratic in Sj square, so it's Gaussian form. And we get something else over here. So the details are not so important. I mean, if you do that to the Laplace, you get that function which is a negative square root, which is convex. You get that dual, and you get that remaining function. So you might wonder how general it is. Does that only work for the Laplace? This is actually a very general thing. You can do that with any scale mixture, and you can do that beyond. I mean, it has to be symmetric, and the log of your potential has to be convex in the square of the variable. Then you can do that. If you plug that in, you get a lower bound on the partition function. Okay, that's what we wanted. Lower bound, here's the partition function. I replace all the Laplacians by these Gaussians. So then I get something that I can actually compute, because it's just a Gaussian integral and something I don't have to integrate over. And the algorithm then is just going to to maximize that lower bound. The lower bound up here. So we've solved the first part of the problem. What is the variational problem here? Well, it's just to maximize this function that I can compute. So then I could do coordinate descent, which has been proposed in 2001 already, which simply means, I fix all the variational parameters except for one, and the update equation is then just a quadratic, very simple to do. You don't need to do anything fancy. It's just an analytic update. And it's a little bit maybe related to what Professor Tiprirani was talking about in the lasso, although it's only in the sense of being a similar algorithm, not the same problem. Now, what is the problem with that? Problem is that that just doesn't scale. So in our application, we have images 256 by 256. So you get 65,000 pixels. And then you have many more filters sitting on the image. I mean, you take differences in both directions, so that already gives you quite a few, and then wavelet coefficient. So we have about 200,000 little potentials sitting on that thing. And if I then would want to run that algorithm on a setup like that, I would have to solve at least q of linear systems of size n. So in contrast to what Professor Tiprirani was talking about, these little steps, these updates for each single site, they are not very simple to do. You need to solve systems. And there's another problem I'm going to talk about later. So anyway, this is out of the question. This is not a problem about buying a bigger computer. This is just really not doable. And you can easily come up with problems where this is millions. So we need something else here. We need scalable algorithms. And these algorithms are just not, in this context, not scalable. They might be in other contexts, but not in this one. So we need to solve that problem much faster, otherwise we can't even go and do that application. So here's a way to do it, and this is very, very recent. I didn't know about this in last February. So we wanna, let's take a negative. It's nicer to minimize things. So let's minimize an upper bound on a negative log partition function, which I just wrote formally here. And if you look at that thing a little bit, then you figure out that it is actually the sum of two parts. The first part is concave, looks like that, in the variable pi. Pi are these variational parameters that we had. And the second part is actually convex, not in pi, but in 1 over pi. So this is just something you have to look at the function. You have to establish that that is the sum of two parts, which have each of them have nice properties. The function as such is not a nice function. I mean, it is not convex, and it does have local minimas and so on. But the point is, for an algorithm, it's important that you decompose it and you see what each of these guys do. So then we are actually doing something that everybody of you knows from the EM algorithm. We are just taking one of them and we are upper bounding it by a linear function. This is basically Legendre duality. That's the second time we need it here. Then we replace that by an upper bound. So we have this guy and this guy here, and then this guy. And now if you look at that, so the reason why the whole thing works now is this is a linear upper bound, but also because z is actually in that Legendre duality, it turns out to can never be negative. This function is not only linear in pi, but it's also convex in 1 over pi. Because 1 over something is convex if you multiply it with non-negative numbers. So then the sum of that was convex anyway, and this is also convex. So now we have a convex problem here. I mean, we have an upper bound which is convex, so we can minimize that thing And if we are lucky, this is actually going to be very simple. And actually, it's going to turn out very simple. I will have that in 2 slides. So the algorithm that you get is a little bit, I mean, really, it's a little bit like EM, although it's probably a bit more difficult to implement it. This you could really see as something like the E step, which means that you have to upper bound a concave part by a line. And the main problem is going to be to compute that set. And I have to talk about that in a minute. And the second part is a bit like the M step in EM. And this is turning out to be a convex problem. I mean, not like in mixture models where you just can write down the solution, but you have to do something a little bit more. But at least it's in principle, it's simple. And I would really say that for many problems, this is basically what scalability means. It means that you can reduce your problems to something that, you know, that other people are very good at doing. I mean, that's, you know, they've been thinking a lot about standardized primitives in numerical mathematics, and now let's use them with our algorithms. I mean, if you manage to reduce your problem to one of theirs, maybe not calling it only once, but several times, then you're really in business. And because then you can just use their code and their knowledge and everything. And this is an important point here. This is despite the fact that, you know, as opposed to what Professor Tipshirani talked about, the sparsity does not come to our rescue here. I mean, these problems are not sparse. This was the second point earlier on what is the difference between these 2 problems. I'm going to talk about that a little bit more in a second. You cannot hope for this to be true, and still you can do this in an efficient way. Let's look at the inner optimization, because this is something that many of you probably know, this algorithm. Inner loop minimization, I mean, don't worry about the details. It's only that I tell you, and the details are then in the paper, that actually it ends up to be a jointly convex function in these 2 variables. This is 1 over pi. I was just calling that now gamma here. And u is basically the variable, the latent variable that I'm in some sense estimating here as well. And this function is a jointly convex one. If you know about convex functions, you see that it's joint convex, although this is kind of an unusual one here. So that means I can actually minimize that in any order. If it's jointly convex, I can do one first and then the other, or the other first and then the second one, and it's always going to be convex no matter what I'm doing. So let's now just eliminate these gammas here. 1 over pi. The remaining problem just has this form. And I'm sure that some of you probably recognize what that is. This is just a reweighted least squares problem. This is something that many of you probably use a lot in statistics for generalized linear model estimation or whatnot. Actually, I have a slide in a second. If you set that to 0, you get the lasso. So this is basically the stuff you have to do in most of the algorithm. It's just iteratively reweighted least squares, and it's very simple to code. This is actually not all my idea. This is inspired by an algorithm which has been used for another problem in just a year ago in NIPS. And I also realized that what they do can actually be done in a much more general way than what I'm doing here. For doing another problem, really. It's not sparse estimation, it's variational inference. Again, let's look at the link to the lasso, because this is interesting. As I said, if you set all these guys to 0, then you get a square root over something quadratic, and that's the absolute value. So you just have the lasso here. A little bit of a difference is that we need to do that more than once. I mean, it's not going to converge in one outer loop iteration. Like EM is not usually converging in one step. It needs a few of them. So technically, we need to do something which is, in this sense, a little bit simpler than the lasso, because this is all differentiable. You can use just the Newton method. But we have to do it several times. Also interesting is that this Z actually controls the sparsity penalty on S. If this is very close to 0, the penalty is strong. If this is further away from 0, this becomes a very smooth function, and there's no big penalty on it. So the algorithm, in a sense, can adjust, how sparse do you want to be in these inner loops. But this is not done artificially by yourself to get the problem solved. This is a part of the whole inference thing. And the algorithmic differences between these 2 problems, sparse estimation, think about Z being 0 in the lasso. This is sparse map estimation. The difference is really that many of these pi's are going to infinity in these problems, or 1 over pi to 0, however you want to think about that, which means that the algorithm forces many of these variables to be exactly 0. That is exactly what you want in sparse estimation, but it's actually not what you want if you do inference, because this means that your covariances are going to be degenerate. I mean, they will have variances 0 all over the place. In approximate inference, basically what we really need is a faithful posterior covariance estimate, and so you don't want to have that property up here. The price you have to pay for that is that these guys actually will remain finite, so sparsity will not come to your rescue. You have to do something else than relying on most of the coefficients to disappear very quickly. Okay, so this is maybe the most technical problem in the whole algorithm you have to do, because I told you how to do the inner loop, which was the convex optimization. I didn't tell you how to refit these upper bounds. And this is basically when the thing kicks in when I say sparsity does not come to the rescue, is this problem here remains. And the problem is it's also a problem that people actually study a lot. It's the problem of computing marginal variances in Gaussian models, in very big Gaussian models. So you have a very big Gaussian random field and you want to know not its marginal mean or its mode, that would be map estimation. You want to know the variances that sit at each variable. This is just another way of writing that. It's basically the diagonal of an inverse matrix here. So you have that matrix, but it's very big, and certainly you cannot invert that thing, and you just want to know the diagonal of it. As I just said, the mean, of such a model is a single linear system, so I would say that this is not too hard to do by algorithms like conjugate gradient algorithms. So you solve, of course, you never solve these systems exactly, you solve them approximately. But you cannot even play tricks like that if you want to have the variance. These are just much harder to approximate. If this is the precision matrix of a graphical Gaussian model, then there are some ways of doing that. Okay, then there are some algorithms that can basically run something like loopy belief propagation, which estimates the variances for you. Well, there are no big guarantees for that, but it works well. In my application, this is certainly not a graphical model precision matrix. It is not even a sparse matrix. This is a matrix that in some sense has some nice structure, but the structure is not sparsity. So I can't use that. So there's one algorithm that you can use in principle to solve this problem, and it's also the only one that I know that in general can address this problem. If you know any other, please let me know. It's the Lensosh algorithm, which is basically something on top of a conjugate gradients method, which basically you can think about. We had a talk about things like that yesterday as an optimal estimator in certain subspaces that you create by multiplying with the A matrix over and over again. So in a sense, these estimators that you get out of the Lensosh algorithm, they are optimal in these subspaces, but they don't cover anything that lies outside of them. I don't really want to talk about this because this looks simple, but it's not technically, and it's a whole different thing. But it's something that other people know a lot about, so we can use that. What you get out in our context is an estimate which importantly approaches the truth from below. So it starts from 0 and it goes up towards the truth in every step. It's also actually essential to do something else in our framework. It is to compute all these design scores I was talking about earlier on for very many candidates, but I'm not going to talk about that. So it's kind of an essential part in our whole method. Bit of a drawback of that method in our context is that the spectrum, so the Lensosh algorithm, this is getting a bit technical here, but I hope you can get away the ideas of that. These matrices, how good the Lensosh algorithm is in approximating anything that depends on the inverse of this matrix depends on how the spectrum decays. I think that might have been said in the talk yesterday. If the spectrum decays geometrically, so that means basically a few eigenvectors of that matrix explain everything, all the variance, you're in a good shape with the Lensosh method. That's exactly the case where it was made for. Turns out in our application, which is probably a bit unusual, this does not happen. The spectrum decays linearly only, which is a really bad case. Basically what it means in statistics terms is that there's information in this matrix that is simply not covered by a few big vectors that basically cover all the variance. You just need a lot of them. You can use a lot of them and you're only ever going to cover a certain fraction of the variance here. What that means is that you can do these land source estimates for a reasonable number of iterations, but you can then also see they are often not very close to the true set at all. And the other problem is because of the fact that the spectrum decays linearly, many of the custom codes actually don't work because they assume that you have a very different spectral behavior, so they do expensive things, so you have to somehow, in some sense, actually at least change these codes, or you have to write your own one to basically address this problem up here. And this is now why the whole thing still works. I mean, this is not an explanation, it's just some ideas. Because I noticed then I did it anyway. And then in practice, I even found that sometimes if you run a smaller number of these steps, of these Lanczos methods, the more steps you run, the better your estimator gets because it's monotonically increasing towards the truth. Now the final result sometimes even gets better if you run less iterations. This is up to some point. If you run very few iterations, it doesn't work. So what is going on here? So maybe, this is, I don't have an explanation for that yet, but I somehow have a bit of an intuition. So the estimator comes from below, and its accuracy increases with k. The sparsity penalty that z vector implies in the inner loop optimization gets stronger if that z is smaller. Remember, if that z was 0, we have the lasso. It's never going to be 0 in our case, but anyway, if it's smaller, it's stronger. So our underestimate leads to the fact that we actually do something that's sparser than what we intended by the model, what we intended the model to do. And in some sense, that seems to counter the fact that the Laplace distribution is maybe not sparse enough to really represent that data well. I mean, this is heuristic, and don't nail me down on this. I still want to try to understand that better. But it's just an empirical observation that, you know, this still works, although the estimators for an important step in the middle are not really close. Once again, you know, if you contrast that whole thing to sparse estimation, I would say that this is actually algorithmically simpler to do because a lot of things become infinite or 0 if you want, even after the very first inner loop, which is just the lasso. And then after that, you get even sparser in these methods. These computations of the Z vector, in a sense, if you have a lot of zeros, this A matrix becomes much smaller. If you look at that for a second, you see that many things, basically, you don't have to deal with that full matrix anymore. You can deal with a smaller one. So in that sense, sparsity comes to the rescue if you do sparse estimation. It doesn't come to the rescue if you do approximate inference, at least not with any method that I know. So this is a slight, you know, towards the theorists. I think that, you know, one of the main motivations for me to be here is basically to maybe get some of you interested in some problems that, I mean, that we use all the time, that work fine, but nobody knows why. So here's one thing that I think is true for sparse, you know, for all the theory that surrounds sparse methods at the moment. They seem to always, in some sense, you know, go in two steps. First of all, they show that something like an L0 regularization, which is the sparsest possible regularization you could do, works very well for what they want to do. And then they basically try to find algorithms that are as sparse as possible. Now, this is nice if you do sparse estimation, but it doesn't really cover what we are doing here. In Bayesian design, we've actually empirically found that if you're too aggressive in the sparsity, this really hurts your performance, down to being really, really bad when you could do much better. This is true. I mean, we did that study for natural images, but this is even true when you have signals that are truly sparse. Okay, so if you want to do things like Bayesian design, you must not be too aggressively sparse. I mean, L0 regularization would be a nightmare here. Second thing is that, you know, natural images are not really sparse. I mean, they are sort of sparse, so you can threshold things to 0 and they look the same. But if you really look at the wavelet coefficient spectra or the Fourier, they never go to 0. I mean, they have a certain behavior, which is a certain decay behavior, but they don't become exactly 0. So what that means is that being too aggressive in sparsification can even hurt your reconstructions. It doesn't only hurt the Bayesian stuff, it also hurts your reconstruction sometimes, because you're not working with truly sparse signals here. Actually, I would even conjecture that no complex real-world signal is truly sparse. I wouldn't know of a natural mechanism that really generates truly sparse signals. So really, the question should be probably phrased a bit broader here. there's a right degree of sparsity, and it's not always maximal degree of sparsity. Certainly, if you talk about natural images, I don't know about other signal classes, even in that sense, even about map estimation or mean estimation, in experimental design in general, being too sparse really hurts you, because here we estimate posterior covariances, and I was already telling you about the problem with sparsity with respect to covariance matrices already. And another thing that would be really nice if people would start to look at methods that at the moment don't really get much attention in theory, because for the simple fact that they are biased. I mean, you cannot show that in the limit they do the right thing. But the point is that they are really heavily used in practice, so we would love to know, especially when do they work versus when they don't work. That is a very important question that is completely open except for empirical studies. And I would say that, this is really also motivated from the theorist side, because if you prove things for true Bayesian inference, then you have to do the Bayesian inference, and there's no way to really do it in practice, because Markov chain Monte Carlo, for many models, it just doesn't work in reasonable time. And then really I would think that if you do very hard theory, which holds in very, nasty worst cases, then you should not really at some point have to hope for something that often is not there. Okay, so this is one slide. Maybe this is some ideas about maybe how our field is a bit different from statistics, but I think it would really help the understanding in, how we could maybe better, in some sense, talk to each other and collaborate. In machine learning, it's really true that I don't know anybody, certainly not me, who is religiously Bayesian. We do Bayesian methods because they really work for the problems that we have, not always, and then we use other methods. And we only do things when they work. But I also have to say that even fewer machine learners believe in minimax results. You cannot do this thing if assumptions do not fully characterize the signals that we work with. And I have to say that I've almost never seen results that fully characterize complex real-world signals. So they almost never do that. So I think in our fields it's even cool to do impossible things. So we are even, if somebody tells us this is impossible, then we have to try whether we can still anyway not do it. So I would think that at least if you talk with machine learners, nothing is wrong about doing strong theory for approximate Bayesian methods, even if you might not believe in them. We probably also don't believe in them, but we just need them for solving our problems. So we would really appreciate strong theory for these methods. And another thing is really that, this is maybe something that is very much, I don't know, maybe everybody believes that Bayesian methods are too expensive, they're intractable. Now, if you approximate them, that doesn't have to be the case, because you can just use the same tricks that people use in optimization for estimation to deal with these methods as well. It's usually a bit more difficult. You run into non-convex problems, but in principle, it's also optimization problems, and so they don't have to be intractable. So let me come to the application I really wanted to do, and this is why I'm doing. Well, at least this is why I went into all this large-scale business. So this is magnetic resonance imaging. It's a type of medical imaging. I'm not going to talk about how this works. It's very fascinating, but I don't have the time. But appreciate that this is really a key technique today for, in hospitals, diagnostics of many sorts, and also in brain research. An interesting point for us who work with statistics and machine learning is that you cannot really throw a lot of money on that problem and then solve it that way. With digital cameras, you can maybe do that. You can just throw money at them, and then you have twice as many megapixels, and that's it. Now, this doesn't work for MRI. There's fundamental limits, and you cannot, reasonably go beyond these limits. So you have to do something more interesting, and that's where maybe statistics comes in, because now you get some data and it's expensive to get it, so maybe you just get as much information out of this data as possible. So formally what happens is that, beyond all sorts of technical constraints, you actually measure Fourier coefficients directly of an image. You don't measure pixels one by one, you measure Fourier coefficients of that image. And these Fourier coefficients, they don't lie all over the place. They lie along piecewise smooth trajectories in the Fourier space. So, for example, here's a Fourier space. spatial frequencies down here. And you know, for example, these trajectories, they lie along that spiral. So this is basically the measurement, you know, machine that you have, and the goal is, of course, to reconstruct these images, these contrasts that you want to see. So this is actually joint work with a couple of people in Tübingen. Hannes Nickisch, PhD student, Rolf Pohmann, who's an MR physicist, and Bernard Scholkopf. We just recently submitted that. So the key idea is here. So if you estimate these images from the data, not using a prior, which is what these people do at the moment, then you're really absolutely stuck with something that is called Nyquist sampling, which is basically one more of these worst case theorems that tell you cannot, if you undersample below that limit, you cannot reconstruct. This is one more of these worst case things. Now you can actually, if you use additional information, which is, for example, very robust priors on natural image statistics, and that really opens up the possibility of sampling sub-Nyquist, which then gets you simply faster, it gets you the same image in less time. So this has come up as a key application of compressed sensing and has already been published, although they didn't really address the fact how would you subsample, because this is not at all obvious, and this is kind of the interesting cases where complicated methods like Bayesian design really come in if it's not obvious for the expert how to do it. It's not obvious because there are tons of things that are not easy to go beyond. One of them is that there's a very strong symmetry in Fourier space. So the signal is actually supposed to be real. So its Fourier transform is Hermitian. So basically you have very strong symmetries with respect to the origin. These natural image priors that we use, they are fine and nice, but they are not explicit distributions. I mean, they only tell you constraints that you would like to have fulfilled. And it's very, very hard to say anything about posteriors or even reconstructions that you get from these priors because they're implicit priors. The reconstructions are very highly nonlinear procedures. They are not simply solving a linear equation, or at least not one that would be accessible before you look at the data a lot with optimization. They are very, in case of MRI, they are very subtle constraints on the X matrix. So you cannot just measure all over the place. You have to follow you have to make sure that the scanner can do it. And you know, you have a huge array of things you can actually do because they tried a lot of things in MRI already. So then let's try to, in a sense, let's try to throw optimization procedure at that problem. So this is a setup now we tried to do as a first setup where we were actually looking at spiral sequences. So spiral sequences, they work like that. They start in the center of the Fourier space and then they radiate out here along this smooth trajectory, and then you go back and you start with a different angle. You see this, there's a second interleaf here. Interleaf is called the single trajectory going out, and these two have different offset angles, so they don't measure the same thing twice. They are nowadays used in very rapid imaging, like if you want to see the heartbeat, or if you want to see blood flow, it's brain imaging. With respect to the signal processing, it's a bit difficult to reconstruct the images because the data doesn't lie on an equispace grid. So you cannot do the fast Fourier transform to reconstruct. You cannot, of course, not do a normal Fourier transform because this is really big signals. So you have to do something in between, which people call gridding. It's been very much research has been put into this basically non-equispaced Fourier transforms. So you could do one thing, which is basically you go after the Nyquist theorem, and if you do that, you need actually 16 interleaves to actually cover that whole range of interest in a Nyquist sense. So the spacing is never above the Nyquist frequency. But if you want to do faster, let's try to do with a half of that number of interleaves. So that would give you an image in half the time. And we do that by actually allowing these offset angles and nothing else just to be adjusted. So each interleaf is just exactly looking the same, but the angle in which you start differs. So for example, one idea you could do is simply to equispace these angles just as you did for the Nyquist setup, which would then give you not a Nyquist coverage anymore because you just have, you would need 16 of them, but you only use 8. You could also draw these angles at random, which is basically what which I would say is something that would be more in line with the CS theory. Or you could design these angles with the method that I was just showing you. And now what do you get? This is very briefly the setup of the whole. This is not yet the full experiment. This is still, in a sense, a simulated one, in the sense that we got real raw data from a scanner, but it has been sampled along an equispaced fine grid in a Nyquist sense. So that is basically the raw data that we start from, and the ground truth of that is simply the absolute value of the inverse Fourier transform. And this is just a fast Fourier transform because the sampling has been done on a grid. And now we basically simulate the measurement from any other trajectory by using these gridding interpolations. So if you would want to do, I mean, the next thing we are going to do is to do this on a real scanner, which would need you to actually really program these spiral trajectories. We are going to do that, but this is a study which just goes prior to that. Now, in theory, if you go from the raw data and you do an inverse transform, you should get a real signal. So you should get a real image. In practice, this doesn't quite work because of lots of sources of error in the magnetic field. So you basically get a phase contribution in that inverse Fourier transform as well. And this is, in a sense, a little bit like the noise that you usually would have in statistics. It's not an additive Gaussian noise. So we could actually work with complex, a model, just putting looking at complex images, putting our priors on that. Drawback of that is that the sub-Gaussianity, if you do that whole thing on a complex image with some phase added to it, then this just becomes weaker. So we didn't want to do that. So we did something else. We remove the biggest part of the phase by just doing a pre-measurement, which would give us then a low frequency estimate of the whole thing, and that gives us a low frequency phase estimate. We subtract that off. We get something where still there are some phase errors in there. And we have done this in different ways, and in the next table, the smaller p, the more noise remains still in these corrected measurements. So if p was 16, you have more noise. P was 64, you have a cleaner, a more corrected signal. And these are the results. So let me explain you this table. All these numbers are L2 reconstruction error. So remember, we have the true image now because we've done this complete scan, and we compare reconstructions against that L2 error. X's are, so these up here, the columns are the different sequences that we use. And down here we have different reconstruction methods that we use given that the sequence was fixed for them. And these guys are here basically the noise level. So this is low noise, middle noise, high noise, in that sense that I was just explaining to you. The reconstruction methods are least square reconstruction, which is basically what they do in MRI reconstruction at the moment. There's something called density compensation in here, so it's really what we do, what these guys are doing. Map reconstruction, which takes the posterior mode from our model. That is the one that has been suggested already in that paper by Lustig et al. I was showing you. And then we can also reconstruct by the posterior mean, which is what our method would probably at least allow us to do. The sequences up here, this is maybe more important. This was the one where you space the angles equally, and which only gives you a Nyquist setup when you use 16 interleaves, but for 8 interleaves you have all these gaps in between. This is just sample these angles at random, uniformly random over O to 2 pi. And this is when we optimize them sequentially for our method. Let me just highlight a few things here. First of all, least square estimation versus map, I think that should really speak for itself. I mean, this is way better here, and the reason why you are way better is basically simply because you use statistics that image really have. This is basically also the whole reason for me why compressed sensing really works on images, is because you get the statistics right, and that helps you a lot when you try to reconstruct them. So here this is just really amazing. Here this is about half the error. Even in the Nyquist setup, you really don't reconstruct very well if you don't look at what the image does. So this looks a bit weird because after the Nyquist theorem you should optimally reconstruct, but don't forget that this is this field of view is smaller, and also the reconstruction is not done in the optimal way. And the third important thing is that there's noise here. There's phase errors remaining. So that's why you don't get I mean, you should get 0 here, but you don't. So let's look at the posterior mean reconstruction across different sequences. This is the main part of the work. I mean, does this really work when we optimize these angles? Now, if you just put them at equispaced, which is maybe a most intuitive thing to do, this is really absolutely the worst thing you can do. And I think my explanation is this because of the symmetries in Fourier space, but certainly it's something that one can improve upon. If you sample them at random, which maybe the compressed sensing theory might suggest, you're doing a bit better, but not so much, and you have a huge variance across the different trials here. This is about, I think, 10 different trials. And if you design them, you get way better. So this design in that context really works. And yeah, so the other thing one should look at is the posterior mean reconstruction, where you compare the thing that has already been suggested, randomize these sequences and everything will be fine, versus designing them with Bayesian design. You can see that there's a huge difference. You can gain a lot by actually designing them instead of sampling them at random. Now here's a lot, here's the difference is not so big anymore. You can be lucky here, but what would worry me is the huge variance here in performance when you randomly sample them. So you quite have to be lucky to hit a lucky case here. Next thing to look at would be, so how is that surprised me a bit. So how is the posterior mean is doing versus the posterior mode? I'm almost wrapping up now. Now actually the short story is the mode actually does better than the mean in this case. I haven't yet an explanation for that, but the important thing for people in practice is that also the mode is very much helped by designing these sequences. Maybe it's helped even more than the mean. Okay. And then maybe the last thing to highlight is really that you can really almost, sample them at half Nyquist limit and still get a reconstruction that's almost as good as if you sample them at the Nyquist limit here. So it really matters how you sample these things. The design really matters, and Nyquist, in some sense, Nyquist doesn't matter that much anymore once you have all these problems like noise and imperfect reconstruction and errors from the scanner. Nyquist matters because in a sense it's a theorem, but in practice all sorts of other things come in. Maybe I just skip over this. This is some reconstructions where you see these arrows here. This is basically Nyquist versus ours. This is randomly drawn. This is actually L2 reconstruction in Nyquist. You see that there's a lot of errors still remaining, which would then, this is basically difference between our reconstruction and truth, right? So you see that this is not a good way of reconstructing. This is, I don't know, interest of time. Conclusions are really that I think, way beyond going plant, science or something, Bayesian experimental design can really help you to solve a lot of problems or to find cheaper solution to problems that supposedly are already optimally solved. If you can get it to run, efficiently enough, that needs approximate inference if you want to do it the Bayesian way, and scalable algorithms have just now recently appeared, and they work because they reduce things to things that primitives people already know about. There's really a direct extension of all of that to generalized linear models. So if you have a non-Gaussian likelihood, you can also use that. And here are the theoretical challenges I think I would like to see, maybe if people are interested, maybe addressing them. I would just want to point out there are important problems that go beyond point estimation with sparsity priors. There is a more complicated role of sparsity when you do other things. For example, if you estimate covariance matrices, then it's not clear that the more sparsity, the better. It's certainly not true. So we have to clarify that somehow. And I think the next thing is, okay, so this is maybe the setup that many people in theory work with. You fix a function class and then you estimate a good candidate. Maybe except for the last talk, I would say that in applications nowadays it's often that is an adaptation as you go. So you really want to have something like experimental design in there, and you would love to have theory about it. So I stop here. Maybe.
Fascinating talk. Is there anyone who wants to make a go off
Yeah, run over time.
into these
Yeah.
Do you use this on complete MR experiments, possibly with thousands of images, or is that on a sort of more single image basis that you pick and choose from a complete experiment?
So I think what you're alluding to is, so there are things that people do with MR images. For example, they model them and they want to find out where the activity is.
Yeah,
This is different. This is lower level. This is reconstructing the image. So it is basically much lower level. I've been thinking about what you could do is that many of these slices, they lie just about next to each other. So you could have sparsity priors going in that direction as well, and you could run a hidden Markov chain on these things. So you could certainly use things like if slices are close to each other, you can even get more out of this. But it's a different level that if you have fMRI images and you want to model them, this is a whole different problem here. This is a reconstructing images, and the criterion is certainly to get a diagnostically useful image for, well, a doctor or brain scientist, and you want to get it faster because temporal, really there are limits on temporal frequency that you have, because and that really depends a lot on how the sequence works. At least that's what I hope for, because this is the whole driving motivation of that thing, is that you can do things really faster and you get results which are still acceptable to the people that work with it. Okay, so you must be careful here that you don't miss, things that are diagnostically important. That's one reason why I'm so happy about these low-level image statistics. I'm not using complicated things here. So I'm not so much likely to miss important activation somewhere, because what I'm using is very benign in that respect. It's just saying that an image has edges and smooth parts instead of being like random noise. But it's different from modeling fMRI images in a statistical way. Maybe the same techniques would work for that as well, but.
So a lot of the classical statistical literature has to do with experimental design, which you have, many variables you're interested in assessing the influence of, and methods also to fractional factorial designs and randomized block designs and things of that nature. And I wonder if that sort of world is relevant in the kinds of things that you see.
I would like to, the thing is I'm not familiar very much with that literature. A little bit I know about design where everything is Gaussian and linear, and I think that would be a big problem for this application because of the reasons that I said. If you can go beyond that, and especially I would be very interested in non-Bayesian ways of doing this, just because I want to see, I'm not a Bayesian by religion, I just, I'm interested in what works, and so I would love to know about, could you do something like that with existing approaches? I've not seen it yet.
I wasn't implying that you could. I was just wondering. Sometimes people have situations there, 20 factors, which could be either high or low, for example. And you want to find some setting which optimizes the response.
I should look more into this. There's some things I glossed over here. For example, is this really the optimization? How am I doing that? It's not at all a convex optimization over these columns of X. So it's, you could maybe look at the literature and find all sorts of tricks. I think an important difference to what many statisticians are doing is that the goal is different here. Is you just want to save on costs. And it's not that you want to, in some sense, in a medical study, you want to faithfully represent some population, and so you have to be very careful about things. You often get data that doesn't really, where the models get more difficult, and then hierarchical models or something. I've been very interested in applications where the model is actually very simple. So MRI is really a linear model. It is one, except for, the error sources, which I didn't talk about. So I think in that sense, if you could use techniques from that field, that would be amazing. I'm just don't know about the literature very much. So if you could point me some out. Then
And reconvene at 2 o'clock for final stellar lecture. In the meantime, did you realize that the program's wonderful origami t-shirt now costs less than a UK government petrol?